Find the volume which results from rotating the region 0 less than or equal to x less than or equal to 1, and 0 less than or equal to y less than or equal to 5 minus 3x over x squared plus 1 times x plus 4 around the line x equals negative 1. So this is a volume of revolution. We have two flavors of volume of revolution. And in this case here, because we're rotating around this line x equals negative 1, we can see that we're rotating here because there's this nice little diagram. And this function here is really this function. It's a function of x, and I don't think I could solve for it. In other words, I don't think I could solve for x here. So I'm going to have to do my little slices here, which means that when I rotate these slices, I'm going to be forming shells. So I'm going to do the shell method. All right, so this is a shell method problem. So shell method, we're going to have 2 pi integral a to b, radius, height, and thickness. That's the parts that go into computing a shell. Now that's 2 pi a to b, 0 to 1. Radius is how far I am from an arbitrary x to the line x equals negative 1. So that's x minus negative 1, known as x plus 1. The height is the value of the function. 5 minus 3x over x squared plus 1 times x plus 4. And the thickness is the dx. All right, so now we have our integral set up. And now we say, well, how do we do it? Well, okay. What is this integral? It's a rational function, which means polynomial over polynomial. And so if I see a rational function, my instinct is to say, all right, what we're going to do here is we're going to do partial fractions. So first thing is check the powers. Upstairs, power is degree 2. So that is to say, if I multiplied it out, the largest power on any term would be 2. Downstairs, it's degree 3. So the reason I'm checking here is I just want to check. If the power was greater than or equal to on the top, then I'd have to do division. I don't have to do division here. So that's good. So we're going to do a little bit of side work here. So I have that x plus 1, 5 minus 3x. I could expand this if I want, but so right now I'll just leave it as is. X squared plus 1, x plus 4 is equal to something, in particular ax plus b over x squared plus 1 plus something over x plus 4. All right. Well, now I need to find my somethings. Well, to find my somethings, I clear my denominator. X plus 1, 5 minus 3x is equal to ax plus b times x plus 4 plus c times x squared plus 1. And now we come to our choice. What do we do? How do we find it? We must make a decision. We must choose. And we're going to choose wisely. There's lots of ways to solve for a, b, and c. The way I like to do it is I like to pick in nice values for x. Anybody have a nice value for x? Negative 4. Great choice. X equals negative 4. So on the left-hand side, negative 4 plus 1 is negative 3. Then I'm going to get 5 minus 3 times minus 4, which is 5 plus 12, which is a big number, 17, is equal to 0 plus c times 17, because that's 4 squared. Negative 4 squared is 16 plus 1. Now notice I have 17s. Well, that's convenient. But it says that c is negative 3. Good. That was a great choice. Is there another good choice? 0. 0 is a great choice. Okay, let's see what happens when we get 0. All right, when we get 0, we're going to get on the left-hand side 1 times 5. 5 equals b times 4. So 4b. And then plus c. But wait, I know c. That's negative 3. So that says 4b is 8. So b is 2. All right, 2 down, 1 to go. Well, are there any other good choices? And the answer is it really doesn't matter. Any choice now will work. Yes?
Well, a plus c equals 0, so you can just say that A is negative Z.
That's true. You can get that. So there are lots of things to do. So as was pointed out, if you look at the coefficients here, is it that A plus C equals 0? Are you sure about that?
Yeah, AX times X, so it'll be AX squared plus CX squared.
Right, equals negative 3x squared. Yeah, so you can compare coefficients. So yeah, you have to be careful. So yeah, there's two things to do. You can plug in values or you can compare coefficients. So if I keep plugging in values, say I plug in negative 1. I don't know. Why not? Well, if I plug in negative 1, what do I get on the left-hand side? I get 0, because x plus 1 would be 0. Okay, then I'm going to get minus a plus 2 times 3 plus 2 times c. Well, that's 2 times negative 3. So if we start moving stuff around, we get 2 minus a times 3 equals 6. 2 minus a equals 2. So what should a be? It should be 0. Now you might say, wait a second, no. A should be negative 0. Close enough. All right, so now we have a, b, and c. So back to our regularly scheduled problem. So our integral becomes 2 pi, integral 0 to 1. I have 0x plus b, which becomes 2 over x squared plus 1, plus c, which is minus 3 over x plus 4 dx. So this becomes 4 pi arctangent x, because 1 over x squared plus 1, that's a good function. You should know that one. You should know. You should predict, like, I wonder if he's going to have an arctangent on this test. Who knows? Log x plus 4. And then we're valuing from 0 to 1. So we're going to get 4 pi, and then we're going to have arctangent of 1, which is pi fourths, minus 6 pi log of 5, subtract 4 pi times arctangent of 0. Arctangent of 0 is 0, minus 6 pi log 4. And you don't have to simplify. You can just sort of leave things as they are. If it doesn't say simplify, you don't have to. So pi squared minus 6 pi log 5 plus 6 pi log 4. And we're done. Okay, number 1. 1 down, 13 to go. We'll probably have to pick up our pace. Any questions? Good. All right, number 2. Set up an integral to find the volume resulting from spinning the region 0 less than or equal to y, less than or equal to e to the minus x squared, and 0 less than or equal to x, less than or equal to 2 around the x-axis. Now, if there were any doubt as to what we're doing, there's a picture. You might be wondering, are they going to give us pictures? And the answer is, pretty much all the time that it makes a difference, we'll give you a picture. All right. So we have to set up an integral. So this one, notice it doesn't say solve, it doesn't say find, just says set up the integral. So I'm integrating here. Now this curve y equals e to the minus x squared. We'll just take it as is. And the natural thing to do is take little slices. And if I spin a slice, what shape do I form? Am I forming a shell or a disk? Forming a disk. So this is the disk method. So the disk method says we're going to have the integral from the endpoint, 0 to 2, pi times the function, which in our case is e to the minus x squared squared, which we can write that as integral 0 to 2 pi e to the minus 2x squared dx. Now the pi doesn't have to be on the inside, but it doesn't matter. It's just pi. Constants are easy to move around. So that's part A. So part A, done. Set it up. Okay, let's go on to part B. Find the Taylor series for the function inside the integral. Cool, Taylor series. We know those things. We know what that means. Now here I see I have e to something, and I recall that e to the generic z, say e to the z, that's a summation, k equals 0 to infinity, of z to the k over k factorial. So in our case, what should z be? Negative 2x squared. So if I take the pi, again, it doesn't matter whether or not you include the pi. The pi is a constant. So pi e to the minus 2x squared would be pi summation k equals 0 to infinity minus 2x squared to the k over k factorial. Which we could go one step further and say, well, what does this really look like? Summation k equals 0 to infinity of, I can put the pi inside, minus 2 to the k, x to the 2k over k factorial. So that is the Taylor series for the function inside the integral from a. They might say, well, why are you doing that? Well, one of the things we didn't point out is there was a reason they told us to set up the integral but not to solve it. The reason they told us to set up the integral but not to solve it is because we can set up the integral, but we can't solve it. We don't know how to integrate e to the negative x squared, because it's just something we don't have. So what we can do is we can approximate it, and that's why there's the Taylor series. Taylor series are approximating the function. So that's why they wanted us to do it. They're really sort of guiding us to say, how would you go about doing this? And the answer is approximation by Taylor series. So we've done part A, we've done part B. Now it says use the first non-zero terms from B to estimate A. So first 4 start at 0. So let's see, what do we have? We're going to talk about the integral from 0 to 2. And then I'm just going to grab the first 4. So k equals 0, I'd have pi. Because something to the 0 is 0, 0 factorial is 1. The next term will be a minus, because they're alternates in sign. I'll have upstairs 2 pi x squared, and downstairs would be, I can write it as 1. 1 factorial. The next term, plus, then I'm going to have 4 pi, because negative 2 squared, that's 4, x to the 4th, divided by 2 factorial, which is 2. Then minus 8 pi x to the 6th, divided by 3 factorial. So that's what I'd get. Now, how do we do this now? We're not actually done yet. We need to estimate the integral. Okay, so we just go through and evaluate, or rather integrate. Pi times x, that's the first term. Here, the next term, add 1. That'll be an x cubed divided by 3, so minus 2/3 pi x cubed. Next one, well, notice I can actually clean this up. 2 factorial is 2, so I can, well, let's put a 2 there. So then it'll be x to the 5th divided by 5. So plus 2 fifths pi x to the 5th. And then for the last one, we're going to have minus, let's see, before we go too far, 3 factorial, that's really 3 times 2. And I can divide through here to make that a 4. So it's going to be minus 4 over 21 pi x to the 7th. Now, what do I do next? I evaluate. From where to where? Well, 0 to 2. And odds are pretty good. It's not going to be great. 2 is kind of far. If I'd gone to 1, I'd be a little bit better. But plug in 0, I get 0. So I just have to plug in 2. 2 pi. Then I have 8. Make it 16/3 pi. 2 to the 5th is 32, so 64/5 pi. 2 to the 7th, of course, is 128. But then you times it by 4, that's 512. So really this is quite a bit off, but that's because we only did the first few terms, and it's an estimate. And that's the answer. You don't have to simplify. Well, that's the process. That's the process. Okay. So that's number 2. All right. Number 3. Find the area inside the polar curve r equals 2 sine theta sine 2 theta for 0 less than or equal to theta less than or equal to pi halves. And not that we really need it, but that's what it looks like. mean, the reason we don't really need it is it gave us the bounds. And perhaps one thing that we can convince ourselves of is it doesn't do something weird where it comes back to the origin early and somehow crossover. No, it just comes out once at 0, comes back at pi over 2. So here we have to think about the area. So area. And we're in polar coordinates, so you have to remember the area formula. So what's the area formula? So area is equal to the 1/2 integral general alpha beta f of theta squared d theta. That's a generic formula. That's if I'm going from some curve down to the origin. So in other words, this is my f of theta. And I'm going straight to the origin at every point. Now, if I was going between two curves, I'd have a difference. Essentially, I would take the larger one, subtract off the smaller one. So in our case, we have 1/2. Alpha and beta become 0, and pi halves. And then I square 2 sine theta sine 2 theta d theta. So at this point, we've really, 2 squared is 4, have transformed it. Say, once you have it set up, so there's 2 phases to most of these problems. The first phase, phase 1, is do you know how to set things up? Phase 2 is where it gets interesting. Now that you've set it up, can you actually integrate it? All right, so we're trying to integrate sine squared of 2 theta. So how do we go about doing such a thing? What can we do? We can do power reduction. Now, one thing we have to be a little bit cautious about, and hopefully you notice this, I'll point it out now, is that these don't actually match up. I have a theta and a 2 theta. That's kind of a dangerous thing. So how can we go about making them match up? Let's get those to match up first before we do anything else. What can I do? There's a couple of things. So first off, let me just to show you. Trigonometry is one of these fun things where there's lots of choices. One thing is you can do power reduction on the first one, as was pointed out. The other thing is you can use double angle identity on the second one. Which one is correct? And the answer is they both work. So do the one that you're comfortable with. Which one do you want to try first? Double angle identity? I'm not saying that that one's better. Just I want to be clear about that. I have no idea. I wrote the problem, but I haven't attempted it yet. So hopefully this is not a bad integral. We're about to find out. Okay. So 2 integral 0 to pi halves. If you use the double angle identity, sine of 2 theta is 2 sine theta cosine theta. So what we'll get, replace it 2 sine theta cosine theta squared. I can square the 2, so that's a 4 coming in with this 2, gets us up to 8. Integral 0 to pi halves. Sine squared, that's sine to the 4th, then a cosine squared. Okay. And now, power reduction. Well, we'll do it. Okay. So what do we do? And the reason, why do we have to do power reduction, by the way? All the powers are even. You really want, you should be, please, math instructors, please, you've really challenged us this whole semester just on the final. Just give us an odd power. Just be odd one time. That's the hope. That's the hope. Okay, so sine to the 4th, we can think of that as sine squared squared. So that's 1 minus cosine 2 theta over 2 squared. And then cosine squared is 1 plus cosine 2 theta all over 2. So, well, kind of regret now going from sine 2 theta to sine theta. Well, whatever. We all get there in the end. Okay. What happens next? Well, we work. So if you look at how many 2's you have actually have enough 2's, because you have 2 squared 2 and 8. So we're to the point where we have 0 to pi halves of 1 minus cosine 2 theta squared, 1 plus cosine 2 theta. And what is this? Well, this is integral 0 to pi halves. And here, notice I have 1 minus, 1 plus. I can write this as, if I take one of these times one of those, I get 1 minus cosine squared of 2 theta, 1 plus cosine, sorry, 1 minus, 1 minus cosine 2 theta. Yes? So I took a 1 minus cosine times a 1 plus cosine, and I got 1 minus cosine squared. Now, why did I do that? Well, 1 minus cosine squared, what is that known as? Sine squared. So, 0 to pi halves, sine squared of 2 theta times 1 minus cosine 2 theta, d theta, which, 0 to pi halves, sine squared of 2 theta minus sine squared of 2 theta cosine 2 theta d theta. Now, this second part, are we okay with that one for now? Yes or no? The answer is yes. We like that one because cosine is by itself. So essentially what you can do now is you can make a substitution. U equals sine, du becomes cosine. So this one is good to go. How about the sine squared 2 theta? Do we like that? No, we do not. So, power reduction one more time, and then we'll actually evaluate. Sine squared, so we get 1/2 minus 1/2 cosine 4 theta minus sine squared 2 theta cosine 2 theta, and all of this is d theta. So we're ready to actually integrate. Integral of a half is a half theta. Integral of a half cosine 4 theta. Well, integral of cosine is sine. You have to compensate for the inside. So because there's a 4 inside, it's going to become a 1/8. And then you say, what about the next term? Well, you just do a little bit of mental math. Again, if u equals sine, you see that du equals 2 cosine. So I have really, moving the 1 to a half, I really have u squared du. So it becomes a u cubed. And so, if you work out the coefficient, because it's a u cubed, you need an over 3, you need an over 2 to compensate for the inside, so it's 1/6 sine cubed 2 theta. Okay. Phew. I was worried we wouldn't have enough space on this page. So that's what you get if you evaluate it. In case you're wondering if these are necessarily the level of difficulty, I will say some are more difficult and some are less difficult than what's on the actual exam. I would say this one, in terms of level of difficulty, maybe it's a little bit more difficult than the kind of thing we'd like to ask. But you should always train with the heavier weights, you know. If you're going to run, you should run uphill. That way when you run on the flat straightaway, you fly. Okay, so now we're ready to evaluate. Nice thing is if you plug in 0, everything goes away. Plug in pi halves. 1/2 times pi halves is pi fourths. Then sine of pi halves times 4 is, well, 2 pi. Sine of 2 pi? 0. Plug in pi halves here, you get sine of pi, which is 0, which means our answer is pi fourths. Okay, that wasn't so bad. All right. Already on to column 2. Well, that was quick. Of course, column 1 had a lot of pictures. So, all right, a special vat. So a special vat, this is a tank, or a container. And it's been formed by taking the curve x equals secant y for 0 less than or equal to y less than or equal to 1/4 pi, and spinning it around the y-axis, all lengths being measured in feet. Currently, the vat is completely full of fluid with density 100 pounds per cubic foot. Find the amount of work to empty the vat of the fluid if the fluid must be raised to the brim of the vat. So, let's draw a picture. I should have drawn a picture that goes with this one. So I have here xy plane, and I'm going to graph x equals secant y. I came very close to saying y equals arcsecant of x, but then I remembered that I said there was no arcsecant. So I said I better not write that. All right, so here's a part of the curve, x equals secant y. So it starts off here at 1, and my picture is inaccurate, but imagine I could draw a picture at pi-4, not that you need to know this, secant of pi-4. Does anybody know that off the top of their heads? Square root of 2. Square root of 2. So what you're doing is you're revolving this around the axis so that our tank looks something like this. So there's our tank, our vat. Except probably won't be lopsided, tilting to one side. Okay, and right now it's completely full. So we have some sort of fluid inside our tank. And we want to figure out what's the amount of work. So, how do we do this? Well, whenever you have work for emptying a tank, the idea is always the same idea. You say, well, let's just think about moving up a small slice. Say we pick a small slice here. Say how much work to move that out. So, the first thing we have to decide is where to put coordinate systems on. Well, this one we don't have to really make any decision. The coordinate system has already been given to us. Because we should use the coordinate system that was used to describe the vat. Now, sometimes we don't give a coordinate system in the problem. We just say, oh, it's a cylinder. Or, oh, it's a cube, or something. And in that case, you have to make a decision. But here, it makes sense to say, look, here is 0, and we'll go up. And that way, we can really describe things very simply. All right. So, how do we figure out the amount of work to raise this level up? Well, that one level, I'm going to look at the distance I have to move it, because work is force times distance. I'm also going to look at the area of the cross-section, the density, and the thickness. I probably should have put density before area, but the point is that area times thickness is volume. Volume times density is mass, or really weight. They're not the same thing. At least that's what my physics friends tell me. I'm just kidding. I don't have physics friends. All right. But this here, that's the force. And then I have distance, and then I add them up. So that's the formula. So now we're just going to go ahead and work through what the formula becomes. Okay, so it's going to be the integral. Well, we have to go to the top, because this time the vat is completely full. If it was only partially full, I'd only go to the level where it's at. But it says completely full, so I'm going to go all the way to the top. So 0 to pi-4. The distance, well, the distance would be from the top to where I'm at. And I'm going to think of this as the y direction. And so what is the distance? Pi-4 minus y. All right. Pi-4 minus y. The area. Well, let's do density first. We'll do density. Because density is easy, because they told us. Right there, they told us. Density is 100. 100. All right, area. Let's talk about area. When we talk about area, we're talking about area of a slice. What do our slices look like? They look like circles. What's the radius of one of these circles? Say I'm at height y. What's the radius? Secant y. So what's the area? Yeah, it's pi secant of y squared. And the thickness, that's your dy. All right, so now we're good to go. Everything is set up. All we have to do is the work. Well, okay, let's think about this. The 100 pi is a constant. Might as well pull that out. So I have 100 pi, integral from 0 to pi fourths. And looking at this, I say, well, I can multiply the secant squared here through. So I have pi fourths times secant squared y minus y secant squared y dy. Now, looking at this, I can't help but feel secant squared, we can integrate that. That's a pretty straightforward thing to integrate. But what happens when I multiply y by secant squared? Can we integrate that? We can if we do integration by parts. So we're going to split this up into two parts. Okay, so let's just do a quick little side note. So this really becomes 100 pi, and then I'm going to have, what is the integral of secant squared? Just tangent, yeah. So pi fourths tangent of y from 0 to pi fourths minus the integral of 0 to pi fourths y secant squared y, dy. Okay, so I'm going to do a little side note and figure out what is the integral of y secant squared y. I think we've done it before, but I find it's hard to remember, hundreds of formulas. It's easier to remember a half a dozen processes. So then I can just figure out, okay, when I need it, I'll just rederive it on the fly. Okay, y secant squared y dy. Which part is going to be the part we integrate? Yeah, so that will become our dv. Which part are we going to differentiate? Well, the reason I'm asking, you guys thought you were like done with that. Yeah, it's fine. Okay, good. All right. So we're going to have that du is simply dy, and v, we said that's tangent of y. So this becomes uv, y tangent of y, minus the integral of v du, tangent of y dy. Well, what is the integral of tangent of y? Log secant. Okay, so that's the integral of y secant squared y. So that's off to the side. All right, back to our regularly scheduled problem. So, by the way, let's just evaluate. Tangent of 0 is 0. Tangent of pi fourths is 1. So, updating 100 pi, and then we have pi fourths minus, and now, you see, I have the antiderivative of y secant squared y, so minus y tangent of y minus log secant of y. I don't need to worry about the plus z, evaluated from 0 to pi fourths. So that's 100 pi fourths minus, plug in pi fourths. Well, pi fourths times tangent of pi fourths is pi fourths minus log of secant of pi fourths. Well, we've already mentioned secant of pi fourths is root 2. So minus log root 2. And then I'm going to subtract, plug in 0. But when I plug in 0, 0 times tangent of 0 is very zero-y. Secant of 0 is 1. Log of 1 is 0. And what do you see here? What happens to the pi fourths? They cancel. Minus minus becomes plus. So our final answer, 100 pi log of root 2. Now, if we wanted to, we could even simplify. What's another thing you can do to log of root 2? You can bring down the half, because it's 2 to the half. So if you bring the half down, you can also write this as 50 pi log 2. And there's the answer. All right. Number 5. Find the arc length of the parametric curve 12 times t plus 1 e to the minus t, comma, 2t cubed plus 3e to the minus 2t. Now you'll see here that we've written it in parametric, which means that this first part here, that's our x of t, and our second part, that's our y of t. So we have our x of t, y of t. So we're looking for arc length, and if we're looking for arc length, we should know the arc length formula. And of course, there's like 3 variations, but they're almost always the same. So the length is the integral from where we start to where we stop, square root x prime squared plus y prime squared dt. All right. Well, this brings us up, this brings us to one of our arch nemeses in calculus, the square root. Okay. Now, should you encounter a square root on the test, I want to assure you, you should not panic. In fact, I'm going to make a very bold declaration that if there is a square root on the test, there is a way to overcome the square root. And I will tell you, it is not the following. Okay, just to be clear. I know that even though I give this word of warning, inevitably someone is going to write this down. The square root of a squared plus b squared is not, I repeat, not, and never has been, and never will be, a plus b. So do not think, aha, I have cracked the code, I know how to get rid of the square root. No. But what you should know is that whatever we give you, something nice will happen. Something beautiful should happen. And I'm going to hope that it's beautiful here. I know that I've been much more careful on the test problems. Even though I can't remember them all, I know that they were actually nice. So, if something is not nice, you've made a mistake. Stop what you're doing and go back. Look for your mistake. Because if you forge ahead, we're not going to go with you. We're going to say, well, enjoy your voyage. Well, we're stopping here. So look for the mistakes. Things should be beautiful. Now, what do I mean by that? Well, let's go ahead and see what happens here. So in some sense, I'm making a bold prediction that this will be a nice answer. I hope that's true after that big setup. Okay, so 0 to 1. Let's do some work over here, x prime of t. So here I have things multiplying together, so I'll use the product rule. So derivative of 12 times t plus 1, that's simply 12, e to the minus t. And then I'm going to have plus 12 t plus 1 times e to the minus t times minus 1 by the chain rule. Now, if you actually look what happens here, you'll see that you actually have a 12 e to the minus t, but it's being subtracted. So they cancel. And what you're left with is minus 12t e to the minus t. So that's what happens when you take the derivative of x. So this is x prime. Something nice. Y prime is simpler because you don't have the two terms mixing together. You get 6t squared minus 6 e to the minus 2t. All right. So, here we go. Square the first term. Minus 12t e to the minus t squared. Plus, square the second term. 6t squared minus 6 e to the minus 2t squared. Now, here is where you want to be careful. So just be patient. Square each piece. So that's 144 t squared e to the minus 2t. Plus, all right, here 6, I square that, it's 36 t to the fourth, which I can maybe write as t squared squared. Now we'll see what happens. Then I have the cross terms. So I'm going to have 2, it's a minus b squared. So a squared, I'm going to have minus 2ab. So that'll become minus 72 t squared e to the minus 2t. Then plus 36 e to the minus 2t squared, which is e to the minus 4t. All right. So When I say nice things should happen, this is where things should happen. If you had sines and cosines, you should get lots of sine squareds and cosine squareds. If you had polynomials, you should get lots of cancellation. If you had to have a weird grab bag of things, you should really get some nice cancellation. Does anything happen nice? And the answer is, something does happen. Those two things combine together. And what used to be minus 72 becomes plus 72. Well, that's really nice. In fact, some people might say, almost too good to be true. Well, why do I say it's almost too good to be true? It's like I took my expression here, where it came from. Whoops. I don't know why I put a parentheses there. Okay, that's just a really big hook on the end. It's a really big hook, dt. See, this was a minus b squared. And the fact that I get a minus there is the a minus b. If I have a plus b squared, I have plus. Well, I do have plus now. So it turns out that what's left becomes a perfect square. So that's the kind of thing that you should expect. What's left is going to be something very nice. All right. Well, equals 0 to 1. Square root and the square will undo each other. 6t squared plus 6e to the minus 2t. And now we can integrate this function. What's the integral of 6t squared? 2t cubed. 6e to the minus 2t? Well, minus 3, e to the minus 2t. And then we're going to evaluate from 0 to 1. So you plug in 1, you're going to get 2 minus 3e to the minus 2. Subtract, when I plug in 0, I'll get 0. And notice, I don't get 0 here. I get e to the 0. So 0 minus minus 3. So not every time when you plug in 0 does everything go to 0. All right, minus minus makes plus. I have 2 plus 3, which makes this 5 minus 3 over e squared. All right. And there we go. Good. Number 6. Well, so far, we've always been motivated by an application. An application led us to an integral where we had to use a technique. We've seen, we've had to do, integration by parts. We've had to do trigonometric integration. We've had to do our algebra and pay attention. And we've had to do partial fractions. We might just say, here's an integral. Let's do it. And then this is our case here. Here's an integral. Let's do it. Arctangent of the cubed root of x. Now, how do we do this? Well, it feels like integration by parts, and certainly we can always, when in doubt, we can always throw in a part by making it a times 1. But I'm not very comfortable with that cubed root of x on the inside. So here's what we can do. Before we even start, let's rewrite. So rewriting is a perfectly reasonable thing to do. So we're going to rewrite by saying u equals the cubed root of x, or if you like, x to the 1/3. And if we do that, then we get that du is 1/3 x to the minus 2/3 dx. Or put another way, dx becomes 3 x to the 2/3 du. Now, I can't substitute dx equals 3x to the 2/3 du because I have to have everything left has to be in terms of u. So what does the x to the 2/3 become? It becomes u squared. So equals 3u squared du. So this, instead of doing this integral, we'll do the integral 3u squared arctangent u du. Okay. And once we're done, whatever our answer is, we will substitute back whatever u needs to be to make it work. All right, well, let's see what happens next. Well, now it's a pretty clear integration by parts. And the reason I say it's a pretty clear integration by parts is because we have multiplication happening. And in particular, this arctangent, that just does not look happy. It's something that we can't integrate easily. But it is something which has a beautiful derivative. So whenever we see a part that has a really terrible antiderivative, or we don't even know how to do an antiderivative, but has a really totally awesome derivative, it's like, let's make that the part where we take a derivative. So the arctangent of u, and now we're going to confuse ourselves because I'll use a capital U, just so we don't confuse ourselves when we talk about u dv. So that's going to be the part we take a derivative of, and then this part is going to be the part that we integrate. So what is capital V? U cubed. And what is d capital U? Derivative of arctangent. 1 over 1 plus u squared. You're probably like, you know what? For the rest of my life, I will never forget the derivative of arctangent. I will tell my children, and they will tell their children's children, passed on through generations. No, it's okay. All right, so arctangent of u times u cubed. So u cubed arctangent of u minus the integral, this one, v, capital V du. So minus the integral u cubed over 1 plus u squared du. Now, we're okay with the first part because we've integrated. There's no integral for the first part. What do we do for the integral of u cubed over 1 plus u squared? We what? Yeah, we divide. We don't do partial fractions yet because look at the powers. It's a cube on the top, it's a square on the bottom. So first thing is, we got to get the powers to be more compatible. Now there's a couple ways to do this. You can do fake long division, or you can do proper long division. And you're probably looking at me like, I don't know what you mean by fake long division. So we won't do that. All right, so we'll do proper long division. U squared plus 1 divided into u cubed plus 0u squared plus 0u plus 0. All right, what do you have to multiply u squared by to get to u cubed? Yes, it's always about u. U cubed plus u, so I'm multiplying u times this whole expression, subtracting, so I'm down to minus u, and then I say, well, wait a second, u squared has a higher power than u, so I'm done with my long division. Well, that was quick. Okay, so what does that tell me? Well, I still have my term in front, u cubed arctangent of u. Then I still have my integral, because I haven't done any integration. What it tells me is that u cubed over 1 plus u squared is the u, that's the part up here. And then my remainder, which is the part down here, over what I divided by. Okay, so that's what we're due. Now, in this case, we're in pretty good shape, because I claim we can do each one of these. And we'll probably even do it in our heads. So, for instance, what's the integral of u? 1/2 u squared. Okay, so minus 1/2 u squared. Okay, now, let's be careful here. Minus minus makes plus. Do we know how to integrate u over 1 plus u squared? What is it? ln of 1 plus u squared. Is there anything else that I forgot to put in here? I forgot the c, but I think there's something else. 1/2, as people have been whispering. Why the 1/2? Well, because really, if you think about it, to get a log, you want the derivative of the bottom to be in the top. The derivative of 1 plus u squared is 2u, but I only have u. So that's why I need to have a half there to compensate. And is it a minus or a plus in front? Plus. Because again, remember that the minus will carry through. It's one of the things that people lose are those signs. Keep track of your signs. When you see parentheses, make sure you multiply those minus signs all the way through. Is that our final answer? No. What's wrong? Yeah, right now it's in terms of u. We want to go back to x. If you have an indefinite integral, whatever variable you start with, that's the variable you need to end with. Okay, so cubed root of x is u. U cubed becomes x. So it becomes x arctangent cubed root of x minus 1/2 cubed root of x squared. So that's x to 2/3 plus 1/2 log 1 plus x to the 2/3 plus c. Now, is this our answer? It is our answer. We're done. Life is good. So now we can say, yes, for sure, we know how to integrate arctangent of cubed root of x. If you ever see it walking down the street, we'll be like, hey, I know how to integrate you. I'm like, whoa. Odds are pretty good you won't see them walking down the street. So now we're going to shift to the latter part of the course. And I will say there's a non-trivial number of problems that come from the latter part of the course. So make sure that though we just did it, make sure you haven't forgotten anything. So find exact value. Now, if you ever see any question that says find the exact value, there are only 3 things that can happen. And we're going to do 2 of them. This is not both, this doesn't have 2 of them in it. But we're going to do 2 of the 3 things that are possible. Do you remember what the 3 things are possible for find exact value? Geometric, telescoping, and you look for Taylor series where you evaluate. That's it. There's nothing else. So whenever you see a question that says find the exact value, you should always be like, I should be looking for one of those 3 things. Okay. Which one is this? Yeah, it's geometric. Now remember that geometric means it's like something to the n. That's sort of the clue of geometric. Now one of the things here is that they can obfuscate. In this case, they really are trying to put 2 things together, thinking it will throw us off. But we are better than that. So it's 2, then times 3/4 to the n, then minus 3 and 2/4 to the n. So that's another way I can write it. 3 to the n over 4 to the n becomes 3/4 to the n. 2 to the n over 4 to the n becomes 2/4 to the n. And this here I can rewrite as really a combination of 2 things. I can think of this as 2 times 3/4 to the n, whatever that turns out to be, as 1 part, then minus summation n equals 0 to infinity 3 1/2 to the n, whatever that part is. All right. Well, let's talk about these sums. For the first sum, what do I get? Yeah, it's 2 over 1 minus 3/4. Now, why the 2? Well, always look at where you start. One of the things that they can do to throw you off the scent is start their sum not at 0. So pay attention. So here our sum starts at 0. So the first term would be 2 times 3/4 to 0, which is 2. Then you divide 1 minus the ratio, 1 minus 3/4. Okay, subtract. And here, what's our first term? 3. Divide by 1 minus 1/2. Okay, so 1 minus 3/4 is a 4th, but it's downstairs, so you flip it, and this first term becomes 8. 1 minus 1/2 is 1/2. That's downstairs. When you flip it, it comes up and becomes 2 times 3, which is 6. So our final answer is 2. All right. Well, that wasn't so bad. Now it's like we're kind of hoping for one of these on the test. Well, maybe. Who knows? 7 questions. All right, so here's another example of find the exact value. So here I have the exact value, summation 0 to infinity, 24 over 9 n squared plus 24n plus 7. All right, well, it's an exact value. So we know it has to be something. Can this be geometric? No, it can't be geometric. There's nothing to the nth. Okay, so that's already knocked out. Does this look like any Taylor series that we know? No. So that's knocked out. So by process of elimination, we should be thinking telescoping. So somehow we need to get some combination of terms. So let's look at what we can do with these. Okay, so 9n squared plus 24n plus 7. What should we be suspicious of? What should we be looking for? Yeah, does it factor? Well, does it? Does it factor? I hope so. Otherwise, it's not going to be as impressive. Okay. So, does everyone see what it factors as? 3n plus what? 3n plus 7 and 3n plus 1? Well, now in some sense it's kind of reasonable to get to that because 7 is, the only way to break 7 apart is 1 times 7. And then in order to really work, you really need to have these almost be the same except for the constant term. The constant is like a shift. So the first term should be both be 3n and 3n. And then we should just check, well, 3n and 21n. Yeah, that adds up to 24n. Okay, all right. So now we get to do something that feels a lot like partial fractions because it's a lot like partial fractions. It is partial fractions. Okay, so let's do some partial fractions work on the side. So we have 24 divided by 3n plus 7 times 3n plus 1. Okay, well that should be something over 3n plus 7 plus something over 3n plus 1. Oops, I don't know why I put parentheses. Well, I'll put parentheses there. Okay, clear my denominators. So 24 is equal to a times 3n plus 1 plus b times 3n plus 7. And now, what comes next? Yeah, there's a couple ways. You can either rearrange or you can pick your n. Well, which one do you want to do? Pick the n. All right, what choice for n would you like? Negative 1/3. And you might say, can I pick any? Of course you can pick any. But be smart. Pick good. You must choose, so you might as well choose wisely. So if I pick n equals negative 1/3, the reason why that's a good choice is it makes something go away. So when I plug in n equals negative 1/3, I get 24. 3 times negative 1/3 is negative 1 plus 1, 0. Gone. Here I'll get negative 1 plus 7 is 6. So 24 equals 6 times b. So b is equal to 4. It's another good choice for n. Negative 7/3. So I plug in negative 7/3. Again, 24. So negative 7/3 times 3 is negative 7. Negative 7 plus 1, negative 6. So I get 24 equals minus 6 times a. So what is a? A is negative 4. Well, that's interesting. Okay. Well, I mean, it is what it is. All right. So we have then, going back to our sum, switch back to green here. So that says that our sum becomes the sum n equals 0 to infinity of, I'll swap the order so I have the positive one first. So 4 over 3n plus 1 minus 4 over 3n plus 7. So this feels right. Because partial fractions, you should have something minus, sorry, not partial fractions, telescoping. Telescoping, you should have something minus something, and you should expect things to start canceling out. So this is good. Now, if you're not sure what's happening, I strongly encourage you, if you're not sure what's happening, when in doubt, look at some partial sums. Look at what the partial sums are doing, and find a pattern. So here, if we carry out the partial sums, well, what do we have? We have 4 over 1 minus 4 over 7, because I'm putting in n equals 0. So 4 over 1, 4 over 7. Then the next term will be 4 over 4 minus 4 over 10, because that's n equals 1. So far, no cancellation. The next term will be 4 over n equals 2. So that'll be 7 minus 4 over 13. And maybe one more, just to convince ourselves that we know what's happening. 4 over 10, 4 over 16. Now, if we stare at this, not very long, we should see something nice. We should see cancellation. Does anything cancel? Yeah, 4 over 7 cancels with 4 over 7. And 4 over 10 cancels with 4 over 10. And in fact, we see, things are going to cancel sort of 2 down. So we're seeing that there's going to be a lot of collapse. Now the other thing that we should see, notice that the terms on the end, the tail, are going to get smaller. If they don't get smaller, pay attention. We have done this in the past where the terms don't get smaller. I remember one test where we were like, does this converge or diverge? And the terms on the tail got bigger. And it actually diverged. And you're like, oh, wait, doesn't it telescope? Yes, it telescopes to infinity. But the terms here on the tail get small, so we're okay. So what's left? Well, the only thing left is the 4 over 1 and the 4 over 4. 4 plus 1, giving us the final answer of 5. So that's the sum, 5. Okay. Number 9. Find the interval of convergence of the sum n equals 7 to infinity, arctangent of n to the n times x to the n over n squared. Now, interval of convergence, do I care about where I start? Does the fact that I start at 7 make any difference to my interval of convergence? The answer is no. No, in fact, it doesn't matter where you start. Really, when you talk about questions about convergence, you always care about the end. It's the part towards the infinity. That's what you care about. So we don't have to worry about where we start. Okay, so when we're doing things like interval of convergence, the way we start these is to say, okay, let's take the ratio test or the root test and figure out what's going on. So in our case, are we better off taking a ratio test or a root test? A root test. And what's the thing that gives away that we should be using a root test? Yeah, these powers of n, particularly this arctangent of n to the n. That's like a clear signal this is a root test problem. So let's do some little work here on the side. So I'm going to take a look at limit n goes to infinity of arctangent of n to the n, absolute value of x to the n, over n squared, all to the 1 over n power, which is the same as the limit as n goes to infinity. If I take the nth root, I'm going to get arctangent of n times absolute value of x divided by n to the 1 over n squared. Well, what happens to these terms? Absolute value of x has nothing with n involved, so nothing happens to that. That's the absolute value of x. What happens to arctangent as we head to infinity? Pi over 2. So this goes to pi over 2. What about this n to the 1 over n? What does that do? Goes to 1. Okay, so we took the absolute value of the nth term to the 1 over nth power and saw that this was the limit. And root test says this will converge when this is less than 1. So I can conclude that it will converge when absolute value of x is less than 2 over pi. Or, put another way, negative 2 over pi less than x less than 2 over pi. Now, is this my interval of convergence? Not yet. Now, it could be, we don't know yet. What we know for sure is for these points here, it will converge. In fact, even more strongly, we know it converges absolutely. We also know that outside of this interval, so in other words, above pi halves or below negative pi halves, it will diverge. What's the only two things we don't know? The endpoints. So, the interval of convergence problems always have two parts. Find the radius in the center, which is essentially this process. The second part is find the endpoints. And by find the endpoints, it's do they get included or not. So, let's plug in one of these numbers. So let's look at this. So suppose I have x equals pi, sorry, not x equals pi, x equals 2 over pi. So I'm looking at the summation, 7 to infinity, of arctangent of n to the nth power, 2 over pi to the nth power divided by n squared. And I'm asking the question, does this converge or diverge? Okay. Now I'll tell you what things won't work. We are guaranteed that the root test and the ratio test will not work. And if the root test or the ratio test work, we've made a mistake. And the reason we're guaranteed that they will fail is because we're at the end. We're at the very edge of convergence. Okay. So we can't use root or ratio test. Alternating series test doesn't apply. This isn't an alternating series. What can we use? Comparison is a pretty good choice here. Now let's think about what's true. So let's think about what's true. This is sort of this one is certainly a little bit more subtle than most, but I like subtle things because it really sort of stretches the mind. What do we know about arctangent of n? What's true about arctangent of n? As we go to infinity, it goes to pi over 2. So what is arctangent of n compared to pi over 2? Is it below pi over 2 or is it above pi over 2? So if we draw the arctangent, and I feel bad, we really should have drawn arctangent more often in this class. What's happening is it looks like this. Here's my pi over 2. I'm getting closer to pi over 2, but I'm getting to pi over 2 from below. So, what's the point? Arctangent of n to the n times 2 over pi to the n has to be below pi over 2 to the n times 2 over pi to the n. Because arctangent's below pi over 2. Well, pi over 2 to the n times 2 over pi to the n, what's another name for that? Yeah, 1 to the n. Also known as 1. So, that tells me that arctangent to the n, arctangent of n to the n, 2 over pi to the n over n squared is below 1 over n squared. Now, so we can make a comparison. This is a good comparison. What do we know about 1 over n squared? It's a p-series, converges. So this is a convergent p-series. And therefore, what's true about this sum? That means it also converges. So this sum converges by comparison test. Okay, cool. So, what does that say about our interval? Do we include or not include? We include. Now let's talk about the other n. If I plug in the other endpoint, which is negative 2 over pi, well, what changes is I just add a negative 1 to the n. So, given that we've already shown that the original sum, without the negative 1 to the n, converges, what's true about this sum? It also converges, because if you take the absolute value, it converges. That's what we just showed, that without that negative 1 to the n, it converges. So this also converges. And so we include that endpoint as well. And therefore, the answer is negative 2 over pi less than or equal to x less than or equal to 2 over pi. And that's the interval of convergence. Now, one of the things that you might notice as you've looked at these problems, and I'll go ahead and say this now, is you might say, you didn't put a lot of problems on, does it converge or diverge, use certain tests, like here's the series. And the reason we don't have to do that is a lot of that is built into these questions about interval of convergence. Because you have to use a root or ratio test, and then you have to use some other tests to figure out the endpoints. So you should be really comfortable with these interval of convergence problems, because these are the types of problems that lets us test many things at once, which is great. We love those. Wow, we're making great progress. I haven't paused for a while and said, are there any questions? How are you doing? Are there any questions? Okay, well, we're about 2/3 the way done, and slightly less than 2/3 the time used. That's a really good thing. I like that. Okay. Find the interval of convergence for the sum n equals 3 to infinity n times 2x plus 5 to the n divided by the root of n cubed minus 1. Okay. Well, what do we start with? What do we do? Should we do a root test or a ratio test? Oh, we can do a root test. Why not? Okay. So, we're going to take a look at the limit as n goes to infinity of, n to the 1 over n, and then 2x plus 5 over n cubed minus 1 to the 1 over n to the half. Okay, so I took the nth root of everything. Now, some of these things are pretty easy. N to the 1 over n is 1. 2x plus 5 is 2x plus 5. And, what about n cubed minus 1 to the 1 over n? What can we say about that? It's 1. I like your attitude. Yes, it's 1. Yeah. I don't think we'd actually force you to go through and verify something like this. But essentially what you should see is n cubed minus 1, what is it really like? In other words, between the n cubed and the minus 1, what really matters? The n cubed, that minus 1 is insignificant. It's really like n cubed. And if I had n cubed to the 1 over n, you would say, yeah, it just goes to 1. You should have that mentality. You should say, look, it basically looks like this. We're about to say that in a few minutes. Like, oh, the minus 1, psh, who needs that? Okay, so this part goes to 1, and so, the limit is just 2x plus 5. Well, that was surprisingly simple. Okay. Well, again, that needs to be less than 1. Where's my center of convergence? Given that absolute value 2x plus 5 less than 1. Can we read that off yet? Yeah. It's a little bit subtle here because of the 2. We'll get more into that in the next problem, I suspect. So let's see. If I multiply, 2x plus 5 has to be between negative 1 and positive 1. I subtract 5 from both sides. So negative 6 is less than 2x is less than negative 4. Divide everything by 2. Negative 3 less than x less than negative 2. Okay, so there's my interval to start with. Between negative 3 and negative 2, I definitely converge between those two values. Outside, we have to think. Okay, so now what comes next? For next, we need to look at the endpoints. Which one do you want to do first? Negative 3 or negative 2? Negative 3? Okay. So 4x equals negative 3. Well, we have the summation of n, and I plug in negative 3. Negative 3 times 2 plus 5. What does that become? Negative 1. Negative 1 to the n. Over cubed root of n cubed minus 1. Well, what does that look like? It's an alternating because of the negative 1 to the n. Now, if I see an alternating series, what do I look for? Do the terms go to 0? Now, there's a technical condition. Do the terms go to 0 in a nice way? We are satisfied if you just say the terms go to 0. If you really want to be like, I have so much free time at the end of this test, I'll go back and spend a half a page explaining why they go to 0 in a nice way. But for us, we just say, look, you're alternating and I see the terms go to 0. By the way, do the terms go to 0? Are we clear on why that's true? What's the power upstairs? 1. What's the power downstairs? 3/2. So the bottom is going to dominate because it has a larger power. So that's how we know it's going to go to 0. So this converges by alternating series test. Now, when you're talking about interval of convergence, you don't care whether it's conditional or absolute. You just care whether does it converge or diverge. You don't care how it converges. So it converges by alternating series test, and just I'll put in parentheses, terms go to 0, just so that people know I actually did some work. Get the full points. All right, let's talk about negative 2. What does the sum become? Well, it's almost the same. What's different? Yeah, there's no minus 1 to the n. So it's just n over square root of n cubed minus 1. Now, when you see that, the minus 1 is a signal, there's a little bit of noise here. But let's just remember, we don't need to worry about the noise. So suppose it weren't there. What do you see? Where does it simplify to? Well, it simplifies to 1 over square root of n. Because you have n to the 3/2 downstairs, there's an n upstairs. So really, it's 1 over square root of n. So that tells us, before we actually verify it or justify it, is this going to converge or diverge? Yeah, it diverges, because we can compare it to a really bad p-series. In particular, now we know that our strategy is to compare it to a bad p-series. Now, if I want to show something diverges, you might remember on the last problem we said, look, it's smaller than something which converges, so life is good. If I want to show something diverges, I want to show it's bigger than something which diverges. So let's just check, is that true? N over square root of n cubed minus 1. Is that bigger than something which diverges? And why? Suppose I do nothing but remove the minus 1. Does my number go up or down if I remove the minus 1? If I remove the minus 1, the denominator increases, but then overall what happens? It's a smaller number. So removing that minus 1, which is why it was a minus, to set it up so that we could easily do a comparison. So this is 1 over root n. So this is a divergent p-series. And now I have something that's bigger than a divergent p-series. So what can I conclude? I can conclude diverges. Diverges by comparison test. All right. So let's go back and finish our answer. So the question is, what's the interval of convergence? We said everything between -3 and -2 is good to go. For -3, do we include or not include? We include because it converges. For -2, do we include or not include? We do not include because it doesn't converge. And that's the answer. -3 less than or equal to x less than -2. All right. Number 11. Find the center and radius of convergence for the following sum. Now you'll notice this is a different type of question. Not all questions are asking us for the interval of convergence. Now you might say, well, why do you only ask for the center and the radius? Well, that's because we might have a sum where it's really hard to decide on the endpoints. And even for us, your faculty members who love mathematics, even we struggle sometimes to figure out what happens on the endpoints. So if you just find the center and radius, just find the center and radius. Don't be like, well, I'm going to spend 2 pages and try to knock out those endpoints. It's not worth it. It's not worth it. Okay, use your time wisely. So here we go. Here, this one involves factorials. So do I use a root test or a ratio test? Ratio. Anytime you see a factorial, you just know it's going to be a ratio test. All right. Okay, so what do? Well, if this is our a sub n, we're going to look at the limit as n goes to infinity of absolute value of a sub n plus 1 over absolute value of a sub n. So this is a little bit of just being patient. And the first step is oftentimes the most important. Remember, I'm going to go through here, and everywhere where I see an n, I'm going to put an n plus 1. So parentheses can be your friend when you're doing this. So n plus 1 factorial squared, absolute value 2x minus 3 to the 3 times n plus 1, divided by 2 to the n plus 1, 2 times n plus 1 factorial. So that's literally everywhere where I had an n, I put in an n plus 1. Then I'm going to divide by a sub n, which is the same as multiplying by the reciprocal of what I started with. So that's 2 to the n, 2n factorial, divided by n factorial squared, absolute value of 2x minus 3 to the n. All right. So at the next step, what we're going to do is clean it up. So for example, when we have exponents, we'll separate it. So 2 to the power n plus 1 is 2 to the n times 2. Factorials will pull off the first, or maybe the first 2, or maybe more. It depends on the factorial, so that we'll get them to line up. So for example, n plus 1 factorial is going to become n plus 1, and then everything else. That's the n factorial. Okay, so this becomes equal to the limit as n goes to infinity of, upstairs I'm going to have n plus 1 squared, n factorial squared. I don't know why I did that way, but that's okay. Absolute value of 2x minus 3 to the 3n. Absolute value of 2x minus 3 to the 3, because 3n plus 3. Then I'm going to have 2 to the n and 2n factorial. Downstairs, 2 to the n, 2, because again, 2 to the n plus 1 becomes 2 to the n times 2. Here I'm going to pull off the first 2 terms off the factorial, so 2n plus 2, 2n plus 1, 2n factorial. Then n factorial squared, absolute value of 2x minus 3 to the n. Sorry, what? I think I'm, to the 3n, yep. You're right, thank you. Phew, good thing you caught that. Check your work. It's easy to make mistakes. Even if you think you've done this for 20 years, you still make mistakes. All right, now the fun part. Cancellation. Those cancel. The 2n factorials cancel. The n factorial squareds cancel. So the 2 to the n's cancel. So that really, it almost all cancels. Well, almost. It doesn't mean everything does. What's left? Let's see. Upstairs, what do we have? Well, we have n plus 1 squared. And we have this absolute value of 2x minus 3 cubed. Downstairs, I have 2 times 2n plus 2 times 2n plus 1. And that's all we have. Okay, so it simplifies to something pretty nice. Now, people have kept asking me this semester, can we just look at the leading powers? See if the powers are the same, look at the coefficients. And the answer is, yeah, that's fine. I'm okay if you do that. So we'll do that. Or you can do L'Hopital's rule, or you can multiply top and bottom by 1 over n squared. Whatever works, just as long as you understand that there is a process. You know what you're doing, and it's not just like, this is a magic box. It's like, I know this box. I can open it up, and I can play with it on the inside. But let's move on and do harder stuff. So, looking at leading coefficients, what do we see? What's the leading coefficient upstairs? So, particularly it's the n squared, and the coefficient of n squared is 1. Downstairs, what's the coefficient of n squared? It's going to be 8. 2 and 2 and 2. So the limit is 1/8 2x minus 3 cubed. Okay, now we're not done yet. So now comes to the next part. We say, well, look, according to the ratio test, this will converge when this is less than 1. So now we start doing our manipulation. We start rearranging. Multiply both sides by 8. So this becomes 2x minus 3 cubed is less than 8. Now what should we do? Cube root. Do we know what the cubed root of 8 is? It's 2. Wow, that's convenient. Okay, so absolute value of 2x minus 3 should be less than 2. So, last thing I can do is I can divide everything by 2. So if I divide everything by 2, that becomes x minus 3/2 is less than 1. Now, why do I say divide everything by 2? Well, in general, if I'm looking for your center and radius of convergence, it should look like this. X minus a less than some value r. This a is your center. This r is your radius. So I wanted to get into the form absolute value of x minus something less than something. Because then I can read off my answer. So I can read off my answer. What's my center? Center is 3/2. What's my radius? It's 1. Because again, 3/2 and 1. And we're done. Because it only asks for center and for radius. So once we find it, we stop. And we move on and do the next problem. All right. So the next problem. So find p sub 2 of x for the Taylor polynomial of f of x equals e to the power x to the 3/2 minus 1 centered at x equals 1. Now it's really tempting to say, hey, this is pretty easy, because I already see there's this minus 1 upstairs. I can just do even better. This asks for Taylor polynomial. Isn't it the case, and you should already tell by the way I'm phrasing things that the answer is no, but isn't it the case that this is just the summation n equals 0 to infinity of x to the 3/2 minus 1 to the k over k factorial? And the answer is, it is the case that that is true, because e to anything is the summation k equals 0 to infinity z, that anything to the k over k factorial. That's true, absolutely 100%. That's true. Is this a series? Or rather, should I say, is this a power series? Now, what is a power series? A power series should be an infinite polynomial. What kind of powers should show up in polynomials? Well, the answer is whole numbers. You should see things like x, x squared, x cubed. You shouldn't see anything 3/2, 9/2, 11/2. So while this is a true statement, unfortunately, this is not the right thing. So we can't just say aha, let's grab it and write the first few terms. But that's okay. If that was like that, that'd be too easy. We don't want things to be too easy. Mind you, I'm not saying I don't want things to be easy. I want things to be easy, just not too easy. We should challenge ourselves a little bit. Well, so let's go back to our definition. So P2 says what? P2 of x, if I'm centered at 1, will be f at 1 plus f prime of 1 times x minus 1 divided by 1 factorial, which is 1, plus f double prime of 1 divided by 2 factorial, which is 2, x minus 1 squared. So this is, just reminding us there is a definition. Work through the definition, do the process. So let's have some fun with our function here. So f of x is e to the x to the 3/2 minus 1. So what's the first derivative look like? Well, it's e to the x to the 3/2 minus 1 times the derivative of x to the 3/2 minus 1. The derivative of x to the 3/2 minus 1 is 3/2 x to the 1/2. Okay, that's not too surprising. What comes next? Second derivative. Because we have to get to the second derivative. Well, so we take the derivative of the first term. That is e to the x to the 3/2 minus 1 times the derivative of x to the 3/2 minus 1, which is 3/2 x to the 1/2, times the 3/2 x to the 1/2 that's already there. Then we're going to add to that the first term, e to the x to the 3/2 minus 1, times the derivative of 3/2 times x to the 1/2, which is 3/2 times 1/2 x to the minus 1/2. Okay. And thankfully, we only are going up to degree 2. If we got up to degree 3, it might take us a while, and I need bigger paper. But that's all right. It'll fit on this page. Okay, now that I have these functions, now what's the next step? Plug in 1, because I need to have these functions evaluated at 1. So, what happens when I plug 1 into here? I get e to the 1 minus 1, which is e to the 0. E to the 0 is 1. When I plug it into the derivative, again, e to the 0, which is 1, times 3/2 times 1. So f prime of 1, 3/2. F double prime of 1. Well, again, e to the 0 is 1. Again, this will be e to the 0. I'll have 3/2 times 1 times 3/2 times 1. So that's 9/4 here, 0. Then I have 3/2 times 1/2, which is another 3/4. 9/4 plus 3/4 adds up to 12/4, also known as 3. So, our desired polynomial is 1, that's f of 1, plus 3/2, which is f prime of 1, times x minus 1, plus f double prime of 1 divided by 2. So that's 3 divided by 2, x minus 1 squared. And that's it. And normally in the past, the next thing would have been, well, how good is your approximation? But what do we know? That's not on the test. Woohoo! Good. Man, thank goodness we filled out some of those surveys. At least we got a few things. Okay. Because I'll tell you, the instructors, we don't like talking about that. It annoys us just as much as it annoys you. Don't tell anybody I said that. We'll edit it out in post-production. Okay. So, winding down. Applications. Now, I will say we've already done an application. So don't forget the application we did before with Taylor series. The Taylor series application we did before is we said, hey, there's this really crazy thing I'm trying to find for volume, so I can approximate what I'm integrating by a Taylor polynomial. That's what we were really doing, is we were saying, there's some crazy thing I have to integrate, Instead of integrating it, I'll approximate it by a polynomial, and whatever that polynomial is, I'll use that instead. So we have already seen an application. That's an application involving integration. So for the end, we're going to practice applications involving differentiation, and then in addition, we're going to work on practicing on manipulating known Taylor series. So here we go. I have the following function. 7x squared cosine of 5x squared minus 4x sine of 3x cubed, and I want to find the 22nd derivative. Now, if we were in a Calc 1 class, oh my gosh, Newton have mercy on our soul. Because we would be here for hours taking derivative after derivative after derivative, and we'd be almost certainly wrong. Because it doesn't take a lot to make a copy error. And I mean, there's stories about people who were a long time ago. There's a story about, we have a few minutes, tangential story, edification. There was someone who said, look, I want to calculate pi. So they spent something like 10, 15 years of their lives doing a computation to compute pi. But the problem was, somewhere around year like 4, they made a small error. And everything else after that was wrong. So they spent, a decade of their life dedicated to computation which was wrong. We don't want to do that. We want to be smart. So what we're going to focus on is being smart. So we're not going to take 22 derivatives. We're going to say, what are these functions? Recalling that Taylor series, store information about derivatives. So the way we're going to start, say, I know something about the generic cosine function. Cosine of a generic z, that's the summation, 0 to infinity, of negative 1 to the k, z to the 2k, divided by 2k factorial. And sine of a generic z value, summation k equals 0 to infinity, of negative 1 to the k, z to the 2k plus 1, over 2k plus 1 factorial. So remember, cosine is the even function, so that's one with the even powers. Sine is an odd function, so that's the one with the odd powers, not a coincidence. So what we're going to do is we're just going to start and say, all right, two things. First off, I'm going to recall that f of x has this generic expression. Sum k equals 0 to infinity of the kth derivative evaluated at 0, x to the k over k factorial. We're going to come back to this in a moment. But I'm also going to note that I can use known series to rewrite this expression. 7x squared cosine of 5x squared minus 4x sine of 3x cubed. So this becomes 7x squared times the summation k equals 0 to infinity of, I'm going to come over here to the cosine one, so that's negative 1 to the k, and wherever I see the z, I'm going to replace it by 5x squared. So 5x squared to the 2k divided by 2k factorial. Minus 4x summation k equals 0 to infinity minus 1 to the k, and then I'm going to have here, everywhere where I see z, I'm going to put the 3x cubed. So 3x cubed to the 2k plus 1 divided by 2k plus 1 factorial. And I'm going to go one step further. Now, let me be clear, one thing I do not have to do is I don't have to force these two into a single sum. That's not my goal. My goal is just to figure out what these things are. It's okay if I leave it as two sums. In fact, it's far easier to leave it as two sums. So, rewriting this, the first sum, I'm going to have the sum k equals 0 to infinity, negative 1 to the k. I'll have the 7 come in. I'll have 5 to the 2k, because I have the 7 come in, the 5 to the 2k. Then I have x to the power 2 to the power 2k. That's x to the 4k plus 2 more. So that's x to the 4k plus 2 more. All divided by 2k factorial. On the second one, I'll write it as plus summation k equals 0 to infinity. I'm going to bring the minus in. So it really becomes minus 1 to the k plus 1, because I had one additional minus come in. I'm going to have a 4 upstairs, coming from the 4. Then I'm going to have 3 to the power 2k plus 1. And then I'm going to have x to the power 6k plus 3 plus 1 more, because there's another x that came in. So 6k plus 4. And all that's being divided by 2k plus 1 factorial. So I now have two expressions for f of x. Which one is correct? And the answer is that they're both correct, and that's the whole point. Now we're ready to answer our question, or at least get the work that gets us to our answer. If I want the 22nd derivative, I see, aha, this is the something that's storing the derivative. And I want the 22nd one. So, what power of x is that attached to? The 22nd power. So, what we're going to do is we are going to grab the coefficient of x to the 22. We're going to do it on both sides. When I say both sides, I mean this expression as the sum of the kth derivative evaluated at 0 and this expression that we found here. So when I look at the power of x to the 22 on the generic expression, I get that it's the 22nd derivative evaluated at 0 divided by 22 factorial. So that's going to be equal to the same thing that happens down here. Do them separately. What choice of k in this sum, because remember, these are two different sums, so don't worry about what the k is on this second sum for now, just the first sum. What choice of k for this first sum will give me x to the power 22? 5. Okay, so I just go through and put in k equals 5. So negative 1 to the 5th is minus 7 times 5 to the 10th divided by 10 factorial. Okay, so just put in k equals 5. Okay, now ignore the first sum. Go to the second sum. What choice of k will give me to the power 22? 3, because I'll have 18 plus 4 is 22. So, again, I'm just care about the coefficient, so I plug in 3. So I'm going to have negative 1 to the 4, which means it's going to be a plus 4 times 3 to the 7th over 7 factorial. And now we're almost done. In fact, the last thing we have to do is we want the 22nd derivative, and I have found this 22nd derivative if you divide it by 22 factorial. So to finish off my answer, what do? Multiply both sides by 22 factorial. So my final answer, negative 7 times 5 to the 10th divided by 10 factorial plus 4 times 3 to the 7th over 7 factorial, that whole thing multiplied by 22 factorial. And that's it. We're done. With this one more to go. So, if you like this one, the next one should be hopefully just as fun. Last problem, number 14. So, we have this function f of x, which is e to the power x squared minus 2x, and I want to find the 50th derivative, but not at 0, at 1. Oh, at 1 you say. Interesting. Because most of our power series have been centered at 0. Well, as they say. What can you do? What can you do? Well, I can't help but notice you have x squared minus 2x. You're probably thinking, of course you can't help but notice it. It says it right there in the problem. You'd have to notice that. Well, the reason I say x squared minus 2x, one of the things that you should think about is say, okay, how does that relate to x minus 1? Now, why do I say x minus 1? Here's the idea. The idea is that we know that f of x can be written as the sum k equals 0 to infinity of the kth derivative evaluated at 1 times x minus 1 to the k over k factorial. That's just a generic expression. Now, what I wrote down before for the previous problem was just when it was evaluated at 0, and then it was x minus 0 to the k. But this holds for any value of a. So here's the thing, is I know I have powers of x minus 1. So I want to look for things that are x minus 1 related. So that's why I say, x squared minus 2x. It kind of feels like something related to x minus 1. Do you see it? X squared minus 2x, what does it feel like? So x squared minus 2x. Think of powers of x minus 1. So what would happen if I added 1 to it? What would you have? It's x minus 1 squared. But I can't just add 1. That's not fair. That seems like we're cheating. So if I'm going to add 1, what else do I need to do? Subtract 1. Okay, so let's see, what we can say. We can say that e to the x squared minus 2x is equal to e to the x minus 1 squared minus 1. Well, that's e to the x minus 1 squared times e to the minus 1. Now, this thing, e to the minus 1, it's a number. And that's perfectly fine. I don't mind numbers. See, numbers are easy to play with. It's when you start having variables attached, that's when we get into trouble. But numbers are easy to play with. Okay, so now that we have this easy to play with number, I'll write as e to the negative 1 is 1 over e. And here is where we say, aha, our great aha moment is coming. E to the z for any choice of z, 0 to infinity, z to the k over k factorial. Here, our choice of z is x minus 1 squared. So this becomes the summation, k equals 0 to infinity, of x minus 1 squared to the k over k factorial. So it's 1 over e, summation, k equals 0 to infinity, of x minus 1 to the 2k over k factorial. So now I've found a way to rewrite my function in terms of x minus 1 to some powers. How do I finish? Well, I want the 50th derivative. So which power of x minus 1 do I care about? The 50th. So I'm going to look at find the coefficient of x minus 1 to the 50th. On the left-hand side, it's going to be the 50th derivative evaluated at 1 divided by 50 factorial. On the right-hand side, we're going to have that 1 over e, because that multiplies by everything. And now, what's our coefficient? Well, which choice of k do I need? 25. And then here comes 1 over 25 factorial. So, we get that the 50th derivative evaluated at 1 is 1 over e times 50 factorial over 25 factorial. Done. And really are done. 14 problems. And we finished it in under 2 hours. The test only has 7. That means you could do the test twice. But really what that means is that you have time to check your work. Be methodical. I really do promise. On every problem on this test, and to a small degree this semester, when you have the problem, the algebra, the simplification, it should become nice at some point. And if it's not becoming nice, take a moment to stop and check your work.